Okay, so uh, as we begin our review, we can look back and consider what we've looked at with physics through all of our study, the science dealing with matter and energy and their interactions. And so throughout this whole year, that's what we've been doing, looking at this, the micro scale all the way down to the fundamental particles like we just did, to the macro scale, to the size of the universe and everything in between. And we've used the case study of the Large Hadron Collider to help us with that. And, we've got the particles smashing together there. And this is a great way to look at, how scientific research is done in a practical way. And so now on the first notes cover page, you have this list. It's important. It'll be important for your review test to remember these. So the first thing, make observations and collect data lead to a question. So in terms of particle physics, they just started to discover these particles coming from the sun, in the middle of the 20th century, and they said, okay, well, there's more than just protons, neutrons, and electrons, and so they started smashing particles together, and all of that energy can turn into mass, E equals mc squared. And that led to many questions, that led to hypothesis, and which led to more experiments, smashing more particles together. And then after they interpret results, sometimes they have to revise what they're thinking, come up with new hypotheses and test those, and then state conclusions. And so a scientist doesn't show up one day and say, okay, I'm doing step 3 today or whatever. What they're doing is very fluid. It's within the whole process, but all scientific investigations follow this progression. What you need to remember with the fundamental units, time is in seconds. It's the SI unit. You need to remember with length is meters. And then mass is kilograms. And it's interesting, at the beginning of the year we talked about how there's physical kilograms. But now they were able to use what we looked at in that silicon sphere, how many atoms there actually are, and use that for the kilogram, and that's going to replace the physical kilogram. So with theories, you need to remember theories try to explain rather, what they see, or what the phenomena that we're looking at, and then laws try to describe. So for instance, like gravity, we know the law of gravity, objects that have mass are attracted to each other. But why that happens, trying to explain that, we're still trying to really figure that out, because, it's part of the standard model where, in terms of, the fundamental forces and all that, but, we still are working, towards understanding that, and there's still questions that are left unanswered here. Now, units are extremely important. You guys remember the Mars Climate Orbiter that crashed because, the instructions were given, but there was no units, and, NASA assumed 1 units, and the engineers gave a different units from the company, then Lockheed Martin, and, it was pretty embarrassing for NASA and for Lockheed. All right, so we're going to get some conversion practice. Go ahead and convert 3,292 seconds into days. You need to set up your brackets, and for credit on the test, you need to do that. 38293 seconds. Now you can set it up like this if you'd rather than full brackets. However, you want to set it up as fine. So go ahead and pause the clip, and let's practice that, and make sure you cross out your units along the way, and when you're ready to check, you can hit play to continue. All right, so seconds cancel out, minutes cancel out, hours cancel out, and we're left with days. So 0.443 days is how long 38,292 seconds is. Now, on your equation sheet, you have the metric prefixes. You don't have to memorize them, which is a good thing. And you just need to be able to use them. And so in this one here, 19,383 meters. We want to convert to megameters. So if you remember, we need to put meters down here, and then we want to get it into megameters. So we see which one's missing the prefix. Megameters, megameters. So we need to put mega in here. And so yeah, go ahead and pause the clip and do this. And when you're ready to check, you can hit play to continue. Okay, so megameters 10 to the 6th. And we should get 0.019383 megameters. Now, when you're doing these, you don't want to forget your logic, right? If you think about it, you know, you're going from 19,383 meters into megameters. Megameters is a big unit, so it's going to get smaller, right? And so, yeah, you don't want to forget your logic as you're going through. Let's practice this one, 16 terabytes into bytes. So go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. All right, so terabytes on the bottom, terabytes on top. Tera is gone. We're left with bytes. 1.6 times 10 to the 13th bytes. Now, and this one is a double conversion, which you're welcome to do all in one line, or if you want to set up 2 brackets, you can do that. Just make sure you show your units canceling out. So go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. Okay, so centi, 10 to the negative second. So we should get 22.15 meters. Then hecto's on the bottom, 0.2215 hectometers. Now, systematic versus random error. If you guys remember, we talked about the neutrinos that they sent through the middle of the Earth, and they thought those neutrinos went faster than the speed of light, which would have broken Einstein's theory of relativity, which is pretty well established now, very well established. And it wasn't until months later, after they even published, that they found that the particles did go faster than the speed, or did not go faster than the speed of light. There was an issue with one of the fiber optic cables and a timing mechanism that were off. And so there was systematic error. There was calibration error there, where they were super precise, but they were off. And so that's systematic error. It's like a triple beam balance that's not calibrated properly, or another instrument that's not calibrated or broken even, can have systematic error, and will set all of the values off. Now, random error, on the other hand, is where we're dealing with outliers in an experiment, and hopefully you get enough data where those outliers are taken care of to where it doesn't skew your results too much. Now, precision, the equipment they were using for the neutrino experiment is extremely precise, to many, many decimal places of the speed of light and the speed of those neutrinos. And so now they were not accurate until they fixed it. And remember, accuracy is how close you are to the standard or accepted value. And that's critical here, getting the difference between those two. Now, frame of reference, we've treated our classroom as still all year, right? And we've done all of our experiments that way, and everything works fine because we've said, okay, we are still relative to the Earth. Now, in reality, if we're outside and we're looking in, let's say we're outside of our solar system, we are going around the sun, and we are rotating around our axis, and so relative to the solar system, yeah, we're moving. And then if we zoomed out even more to the Milky Way, right, we're spiraling in the Milky Way. So again, it's all a matter of the frame of reference, how we have to talk about motion. All right, so let's go ahead and practice a displacement problem. And yeah, this is the first coded one here. You can go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. Okay. So out to 12, back to 9, 15 meters is the distance, and then remember displacement is x finals minus x initial, and so the displacement would be positive 9, and then the total distance would be 15 meters. All right, speed, right, is the distance that you have in time, and we're looking at meters per second. and then velocity is the displacement in time. And we've got that. Now, the final step that I want us to do, or final thing today, is let's say that we're walking, and let's mark these out here. Let's say that each of these markings represents 1 second. And let's say each of these spaces is 2 meters. 2 meters, 2 meters. What I want you to do is draw a position time graph and a velocity time graph for the person walking. So if you want to pause the clip and give that a try, and when you're ready to check, you can hit play to continue. All right, so if we set up 1 second, 2 seconds, 3 seconds. In 1 second, we're going to go 2 meters. Then after the next second will be at the 4 meters. So our graph will look something like this as it goes up here, here. And then if we get the slope of this, we're going to get 2 meters per second. So that's going to be here, 2 meters per second over the time. And that's good.